Alright, students, let's review question 11 from the reaction mechanism tutorial. Okay, so we have question 11a. You are given this particular reaction. Okay, so it reads when ethanol reacts with dilute sodium hydroxide at room temperature, dimerization occurs. Okay, so some form of dimerization occurs, produces 2-hydroxybutanol as illustrated below. So below, the reaction scheme gives you the formation of 3-hydroxybutanol. And you were told that 3-hydroxybutanol is both an aldehyde and an alcohol. Okay, so how can we notice that? There's an aldehyde group over here, and there is a secondary alcohol over here. Yeah, so this particular product is known as an aldol. Okay, and this kind of reaction is known as an aldol addition. Okay, so from ethanol, when two ethanol molecules react, it gives you 3-hydroxybutanol. This is known as an aldol addition. And then after heating it, you realize that the H2O is being removed from 3-hydroxybutanol. So you end up with something known as but2-enal. Okay, so the condensed structure formula is written like this. It might be a little bit confusing for some of you. So it might be easier if you just write out the skeletal structure. Okay, so I have a methyl group, and then I have a CH, so that will be a double bond, and then this is followed by the aldehyde functional group. Okay, yeah. So what you are getting here is an aldehyde that is conjugated. Okay, so I'm going to show you the conjugation. Okay, so this is a CC double bond conjugated with a CO double bond over here. Yeah, so this kind of conjugated aldehyde system is very stable. If you read ahead from university text, this is known as an alpha-beta unsaturated carbonyl. Okay, so alpha-beta unsaturated carbonyl. Okay, if you're interested, you may want to read up a little bit more about alpha-beta unsaturated carbonyl as well as aldol reaction as part of your own academic enrichment. We're not saying that it is in your H3 curriculum, but I think what we are really saying is that if you read up more, you get more familiar with such reactions. I think it will help you a little bit more when you digest information given to you for assessment purposes. Yeah, but do read up only for interest. If you read up solely for the sake of wanting to do well in exam, then don't force ourselves to do that. Yeah, I think it's better if you get intrinsically motivated to read up more solely because you are interested in the subjects. Okay, yeah. Then why is it called alpha-beta unsaturated carbonyl? In case you want to know lah. Yeah, because this particular carbon is known as the alpha carbon, and then the carbon next to it is called the beta carbon. Yeah, so the alpha and beta carbon becomes a CC double bond, and it is conjugated with the CO double bond. So yeah, so it's a conjugated system. Yeah, so over here, I think it's mentioned that the product is stabilized by having a conjugated double bonds. Okay, so we have part 1. The reaction occurs at the alpha hydrogens on ethanol, unusually acidic. Okay, so this is the keywords, unusually acidic. With the aid of appropriate diagrams, explain why this is so. Yeah, this is a very popular way of asking questions with the aid of appropriate diagrams. So it depends on whether you are looking at it from the H2 or H3 perspective, because that determines the depth of your answer. Okay, but without going into further details at this point in time, right? Let us focus on the word unusually acidic. Yeah, so what they want you to sort of mention is that that means that the alpha H tends to be lost And based on what you learn from acid-base equilibrium, if the H tends to be lost, that means that the conjugate base is somewhat stabilized. Okay, so maybe we can attempt to draw out the conjugate base below, in the space below. Okay, so we know that ethanol has this particular structure. Okay, and you have a CO double bond and an H here. Okay, and if the H is being lost, we can actually write out this particular equilibrium. Okay, and then with a lone pair here and a minus charge and a C double bond OH. Okay, so what we are saying, what we are really saying is that this particular conjugate base, right, it's more stable than a usual sp3 or sp2ch where the H is being lost as a proton. Yeah, so what we are saying here is that this is particularly stable. How can we understand it? You might understand it by looking or by noticing that there's a CO double bond here, where it's a electron withdrawing group, and the electron withdrawing group will help to withdraw electron density away from the negatively charged center, so thereby stabilizing it. Yeah, so that is a first level analysis from a typical H2 perspective. Yeah, but if you want to go a little bit more in depth, let's say maybe a stronger H2 kind of answer, then you might want to consider drawing in an orbital diagram showing the overlap between the unhybridized p orbital. So I'm going to draw this out. Okay, so I'm going to show the geometry around the carbon bearing the negative charge. Okay, it's likely going to be trigonal planar. Okay, why is it likely to be trigonal planar? Because if it's trigonal planar, then it's likely to overlap well with the CO pi system. Okay, so I'm just going to draw in this pi bond. Okay, so you notice that being trigonal planar, right, the lone pairs of electrons is located largely at the p orbital, or it has the p orbital characteristics. So this allows it to overlap continuously with the CO pi system. Okay, so this particular continuous overlap, right, is what we normally in H2 we say that the lone pairs of electrons is delocalized over to the CO pi bond. Okay, so this is normally what we'll write in H2 . So lone pair of electrons on the negative charge, or on the carbon bearing the negative charge, okay, is delocalized over to the CO pi system. Yeah, okay, so this particular diagram, right, allows you to use a diagram to kind of represent what you want to explain in words. Lone pairs of electrons delocalized over to the CO pi system. Yeah, but what if we want to use a more advanced approach, which is what you have learned in H3. Okay, so a slightly more advanced approach will be to draw out the resonance structure. Okay, so in order to draw a resonance structures, what we can do is I can simply just start from here. Okay, so the lone pairs can delocalize, so I'm going to form the C pi bond, and then the CO pi bond will now break towards the oxygen. Okay, so remember that resonance structures is shown with a double arrowhead. Okay, so what I'm going to get here is something like this. Okay, and then with a O minus and a H here. Okay, so this showcase the delocalization of the lone pairs of electrons over to the CO pi system, and now the oxygen will gain the negative charge. Okay, so what we form here, right, is what we call an enolate. So this is known as an enolate. Okay, yeah. So if you want to form back the one in green, you can simply just push back the electrons from the CO from the O minus at the oxygen, and then I'm going to form the negative charge, or the negative charge will now appear on the carbon, or on the sp2 hybridized carbon, or you can call it the alpha carbon. Okay, yeah. So several ways you can represent your answer. So so for one, using appropriate diagrams. What kind of diagrams are we expecting? You can show resonance structures, if it's a more H3 kind of questions, or you can simply show the orbital overlap if it's a more H2 kind of question you'll see from some of the prelim questions or even the A-level questions. Right? Okay, and then for part 2, suggest the reaction mechanism to the Aldol reaction shown above. Explain whether you expect the resultant products to rotate plane polarized light. Okay, so what exactly is happening here is that okay, so I'm just going to erase some of these parts to make it easier. Okay, and also to save a little bit of space for me to work on the questions later on. Okay, yep. Okay, I'm just going to erase this as well as the orbital diagram because I don't think it's necessary to showcase it in our part 2 answer. Okay, so you notice that the question requires us to show the mechanism of the Aldol addition to give us 3-hydroxybutanol. Okay, so what we can do here is I'm going to use OH minus because that is the base given to me. And remember that when you push electrons, you should push it from the source all the way to the sink. Okay, so the lone pairs of electrons attack this H here because this is the acidic protons. Okay, and I'm going to break the CH sigma bond heterolytically, and then you'll allow the alpha carbon to take on the negative charge. Okay, yeah, so this is one way we can do that. Yeah, but remember that when we push electron density, right, an ideal way is to push it all the way to the electron sink. Yeah, so the carbon can't be the electron sink. The electron sink should be the carbonyl oxygen. Yeah, so a slightly more ideal way of pushing electron density, right, is really to push it all the way to the sink. And straight away we should draw out the enolate form. Okay, so we should be drawing out this, and this is the most ideal way of showcasing the mechanism. Okay, so I'm going to remove the double arrowheads. Yep, and then I'm going to straight away show the enolates being formed. Okay, so the enolate will simply be like this, like this. Okay, O minus with a H here. Okay, yeah, so this is the enolate being formed, and you notice that the enolate being formed, right? As what we have seen earlier on, if you draw the resonance structures out, right, then it is nucleophilic at the alpha carbon. Okay, it is nucleophilic at the alpha carbon. So if you can't really see it, yeah, so it is perfectly fine to simply just push it to the alpha carbon, where the alpha carbon bears the negative charge, as what we had shown earlier on, so that you know that it is the nucleophilic carbon. But if it is okay for you, then I think you should leave it in the enolate form, so that later on, when you push electrons to allow nucleophilic addition to take place to give you 3-hydroxybutanol, then it makes a little bit more sense if you push it the way it does. Okay, so I'm just going to showcase it from the enolate form. Okay, so I'm just going to erase this portion. Yeah, the reason why I drew out the resonance structures earlier on is really just to show you that the carbon, or the alpha carbon, is the one that is nucleophilic. Okay, so what's going to happen here is that I'm going to show another ethanol. Okay, usually in H2 we put delta plus, delta minus. Okay, so I'm going to showcase the pushing. Okay, yeah, I'm going to draw in red. Okay, so I'm going to push it to form the CO double bond, and then the pi bond will not attack the carbonyl carbon, and then the CO pi bond will break. Yeah, you'll notice that this particular reaction is simply a nucleophilic addition, which it should be quite familiar to most of you. It's not something which is very unfamiliar to you. Okay, so if you have difficulty visualizing it, you can, as I said earlier on, start off from the alpha carbon bearing the negative charge. I mean, if you're okay, then you're okay with it. So in order to be able to sketch out or the correct structure, it's helpful if you can number the carbon. So that's 1, 2, 3 and 4. Okay, so you know that carbon 3 will be the one forming the secondary alcohol. Okay, so with that, I think it's a lot easier. So I'm going to just draw it directly. So I'm going to have a CO here. double bond H, so that's carbon 1, 2, and then carbon 3 will be the one forming the alcohol. But it will start off with an O minus because an alkoxide is being formed first. Okay, so if I'm going to number the carbon, that will be 1, 2, 3, 4. Okay, then if the reaction is going to continue, you notice that it is being done in somewhat an aqueous medium. Okay, it's an aqueous medium. So, and you know that in aqueous medium, the stronger base must not be anything stronger than hydroxide. So therefore, the deprotonation of water is probably the next step which you want to take. Okay, so the lone pair will then attack the H, and then it will break towards the oxygen. Okay, and then that's how you will get the hydroxyl ethanol. Okay, something like this. Okay, so you are simply asked to draw the nucleophilic addition product or the Aldol addition product. Okay, you can leave it as it is, right? And then you are asked to explain whether the resultant products is able to rotate plane polarized lights. You notice that a chiral center is being produced here, but I do not expect it to rotate plane polarized lights. Why is that the case? If you recall from your H2 topic 17 on carbonyl, as well as our H3 lecture notes on reaction mechanism, you will notice that the nucleophile approaches the carbonyl carbon from the top and bottom plane with near equal probability. So what you end up with is likely to be a racemic mixture. Okay, so I don't think you should expect any form of rotation of plane polarized light because I'm forming an equal amount of both enantiomer. Yeah, of course there is a way for you to control it, but I think that comes later on, which we will tell you more lah. If you you probably need to use to control it using some catalyst or some metal to chelate or to bind the units together, but that's later on. But in our case here, there isn't any extra reactants or there is no additional chiral centers involved, so I don't think you will expect any rotation of plane polarized lights. Yeah, of course, the if you heard me earlier on, you will notice that in the formation of a product with one chiral center, especially when the approach is near equal probability, right? The transition state is likely to be enantiomeric. So enantiomeric transition state has the same electronic energy. So there is no way to differentiate the two. Yeah. So in that sense, I'm not going to expect an abundance of either of the enantiomer. Yeah. If I started off with a reactant with already a well-defined chiral center, then yes, I would expect some form of differentiation because the transition states is not enantiomeric, but it is diastereomeric. So there is some difference in the electronic energies. Yeah, but you do not usually need to worry about that when you're dealing with H3 at this level. Okay, unless you are talking about university kind of concepts, or you learn more stuff in university and you have to take all these things into considerations. Okay, then for part 3 is an application of what we learned earlier on. Usually when it's under the same large part like part A, B, right, the subparts are usually related. So you are being asked to suggest suitable reagents and conditions that you use to synthesize compound B from A in a clearly written reaction scheme. Yeah, some students went to draw the mechanism, but maybe let me emphasize that the drawing of mechanism is absolutely unnecessary because it's really not needed. Because you are just required to write down a reaction scheme. That means that it's your usual H2 when you incorporate the reagents and conditions and then draw the intermediate products. Okay, yeah. So what we notice here is that the number of carbon didn't change. The number of carbon remains as 10 if you do a quick count. On the left hand side, you have 2 fused 6-membered ring, and then so you have 6 plus 4, 10. And then on the right hand side, you have a fused 5-membered ring and a 7-membered ring. So if you add them up, again, it's 7 plus 3 is 10. Okay, but what we notice here is that this is a alpha beta unsaturated carbonyl, if you noticed. Yeah, so this is quite characteristic. it's something which we might want to pay attention to. Yeah, because from our earlier reaction scheme, the alpha beta unsaturated carbonyl is formed from a dehydration kind of reaction. Yeah, so I expect before I form B, my precursor is likely to be an Aldol product. Okay, so I'm going to draw my precursor out. So I'm going to draw the 7-membered ring. Okay, just draw it nicely. Okay, double bond O. Okay, and then an OH over here. Okay, so this is the OH over here. Okay, yep. Okay, so I hope that makes sense to you lah, because if you look at all the different scenarios, you notice that the OH is being found in the beta carbon, and the beta carbon essentially is here. Okay, so this is alpha, this is beta. Okay, so I'm just following what we have. Yeah, so basically in order, to go from the aldol to the dehydrated product, we just need to heat. So here I can just simply put heat. Okay, I don't have to do anything else. Then how do we get the aldol product? Yeah, so to get the aldol product, probably you expect some form of aldol addition reaction. Yeah, but for the earlier examples, we have two molecules coming together, but in our examples we have two fused ring. So therefore I expect probably it's an internal aldol reaction kind of we should expect internal kind of aldol reaction. And because this carbon this particular beta carbon is the one having the OH, so probably we expect this particular carbon to be the original carbonyl carbon, and then this particular carbon to be the alpha carbon where it is being deprotonated. Okay, so if I'm going to number the carbon together, I'm just going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So I expect carbon number 10 to be the alpha carbon, which is being deprotonated to form the enolates, which will then perform a nucleophilic addition on carbon number 6, where carbon number 6 is the carbonyl carbon. Okay, so if we expect that, then I can then draw out the precursor to this. So if I draw the precursor to this, I can simply just try to draw something ugly. Okay, let me see, 3, 4, 5, 6, and then after that 9, 8, 7. Okay, so this doesn't look so nice. Okay, so I'm just going to number it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I'm going to draw out the double bond O. So this is the double bond oxygen, and then carbon number 6 will be another double bond oxygen. Okay, and then should I be drawing out the enolates? Okay, maybe if you want, you could. You know that I have to deprotonate this carbon number 10 in order for me to perform a nucleophilic addition to give me the aldol addition products. But if you don't wish to draw this out, it's okay. Okay, but this is just something for you to take note of. Yeah. So if I put the negative charge there, then you know that the precursor, obviously, I can't have the negative charge because this is a reactive intermediate. Yeah. So based on what I have earlier on, the reagents is simply sodium hydroxide aqueous at room temperature. So I'm just going to put sodium hydroxide aqueous at room temperature, which is 25 degrees Celsius. Okay. Then how do I get from A to this particular product? Okay, you might be wondering. Yeah, so if I'm going to number the carbon, you realize that carbon 1 and 6 originally is bonded with a CC double bond, so it's some form of oxidative cleavage. How do we come to terms with that? Well, how do you get a dicarbonyl from two fused ring with a CC double bond? Just think about it based on all the reactions you have learned. Okay, so if you just number the carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you realize that it makes sense, right? If I'm going to cleave this, then I'm going to end up with carbon 1 and 6 having the CO double bond. Okay, so with that, then I'm able to write out the reagents and conditions here. I think it's not something which is difficult for most of you, or if not all of you. KMnO4 equals acidified with H2SO4, and then I'm going to heat it. Okay, so oxidative cleavage will take place. Alright, okay, so with that, I think we are pretty much done with part A. I hope this particular review gives you a little bit more insight into how such questions can be attempted. Okay, next we'll move on to part B, which is more challenging, in fact. But you have a diagram to guide you in your thought process, so it should not be as challenging as you think it is. Okay, so if you read part B, right, one of the ways in which the stereochemistry of the Aldol products can be controlled is to employ either Z or E enolates in the synthesis. So this has been predefined for you. Okay, so you were told the Z enolate is given here. Okay, and then the examples are given below. And then of course you have the E enolate. Okay, and then examples are given below as well. Okay, and then you were told, you were given some details like R is a chiral alkyl groups. Yeah, that means that the transition state is likely to be in diastereomeric because the chirality is predefined. M is a metal ion and L is what we call ligands. I know ligand is not something which you have learned before, but you would have heard about it in the course of your qualitative analysis practicals. Like for example, water is a ligand to most of the transition aqueous ions, transition metal aqueous ions. Okay, but never mind about that, because since it's predefined for you, all you need to do is just to go through the pictures, the diagrams given below, so you can understand a little bit about what's going on. Okay, so in the story below, right, you were told that when ethanol reacts with the Z enolate, the syn product predominates as the reaction is thought to go through a chair-like transition state. Okay, so this has already been established in the scientific community. Yeah, so it's now being given to you as an information which you are required to apply it and in the solving of the questions later on. Yeah. If you want to read up more about this, it's usually in some more advanced level textbooks on asymmetric synthesis. Yeah. It has a name. It's called the Zimmermann-Traxler transition state, but I don't think you want to go into details at this stage. Okay, so if you are interested, you can just read up more. If not, I think you can, it is perfectly fine to leave it as it is. Okay, yeah. Then, so yeah, given, you do not really need to question whether this is correct or wrong. That's not the point we are trying to say here. But what you should probably be doing is to apply the information given to you to answer the questions later on. Okay, of course you can question it, no issues, as in but remember that in a question especially in an exam setting, right, I think your role is more to apply the information given to you on this on the scenario, so that it's easier for you in problem solving. Okay, yeah, but I would like to maybe bring to your attention things like some of the terminology used in asymmetric synthesis, like for example, the syn product. What exactly do we mean by the syn product? Okay, the syn product is when you draw the structures in this skeletal format, right? You notice that the two groups in question are bonded to the chiral center being formed. In this case, it's the alpha and beta one. They are pointing away or towards you in the same direction. That's what we call syn. Okay, so if it's anti, right, that means that it's pointing in opposite direction. Okay, yeah. So for part 1, right, you are asked to draw the anti-products and use the above idea to show how the anti-products might be obtained from Z enolate. Okay, so the first thing we would like to establish, or maybe we should establish in is how do we visualize this particular diagrams and how it can help us to problem solved. Okay, so the first thing you might want to notice is that you'll notice that the R group is trans to the CH3. That's very important. And it's being trans to CH3, it must also be shown up in the transition state. Okay, this is of extreme importance to ensure that you draw the correct thing. So that means that later on, right, if you are using the E-enolate, right, that means that the methyl group must be found in the equatorial position. Yeah, so that is something which is important, and you need to recognize that. Okay, so once you recognize that, then I think I will just erase this. Okay, then another thing you might want to recognize is that this is an enolate. So an enolate meaning that if I'm just going to remove the metal, right, it will actually look like this. It's an O minus with an R group, and then a double bond and a CH3. So it will behave in the same way as what we have established earlier on. That means that the alpha carbon is the nucleophilic carbon. Okay, so we have to establish that. Okay, so that means that in the course of a reaction, right, the pi bond of the CO will be reformed, and then the alpha carbon will be the one attacking an electron deficient site. So it will work the same way as what we expected earlier on. Yeah, so if you can understand this, that means that you should be able to understand why this bond is being formed. Yeah, because if you don't understand why this bond is being formed, then sometimes I think the students will get confused. Yeah, that's what happened to your seniors in the past. They get confused on how come there's a dotted line here. So this dotted line actually tells us that the CO bond, the CC bond is being formed because the enolate carbon, right, performs a nucleophilic attack on the carbonyl carbon. Yeah, and then in the process, it will cause the carbonyl CO bond to break towards the oxygen. Okay, and then another thing which your senior don't quite understand, it's more of how come the metal, right, is coordinating to both. Okay, so this I can explain in some details. The reason why the metal is coordinating to both, right, is because this is how catalysis takes place. So remember something which you have often learned in H2 is that intramolecular reaction happens faster than intermolecular reaction. And the reason why that is the case, right, is because for intramolecular reaction, right, the system is already binded as a whole loop. It is within itself. You don't need probability of collision between two species which are likely to be far apart. Yeah, so it is often the example I use when I explain to students. It's like it's easier for you to slap yourself as opposed to your friend slapping you, or it's easier for you to hit yourself as opposed to your friend hitting you. The reason is you are behaving as an intramolecular system, whereas if you need your friend to hit you, that will be behaving as an intermolecular system. Yeah, so the reason why catalysis or reaction with a catalyst inside is faster, right, is because the metal is able to coordinate the two species, bring them together, and forces out an intramolecular reaction. And in this case, the metal is the one which coordinates between the enolates and the aldehydes and bring them close to each other, and they behave as though they are in an intramolecular system reacting rather than the collision between an enolate and an aldehyde. So that makes the reaction a lot faster. Okay, so I hope you are able to understand this a little bit more. Okay, and also do take note that the transition state being drawn here is not like the most accurate version, because it doesn't show you the partial bond breaking between the CO, etc., and the CC double bond, but it's just a cartoon kind of illustration. And also bearing in mind that this question was from many years ago, and back then your seniors did not learn much about transition states. Okay, so do bear in mind with the quality of the cartoon, although it doesn't really represent reality. But what I can share with you here is that this diagram itself, it is okay as it is, and it's able to tell you how the syn product is being produced or is being predicted. Okay, yeah. Okay, so anyway, okay, so this is what it is. I've already explained the role of the metal. And you might be wondering, some students will end up wondering, how come I end up with a syn? Okay, so what I can do is I'm just going to draw up a very rough structures above on after the whole reaction, what this whole thing is likely to look like. Okay, it's just an ugly version, so please bear with me. Sometimes I can't stand myself drawing very ugly stuff. Okay, so I'm going to have an R here. Okay, remember that in the course of reaction, after the whole reaction, right, this will become a C double bond O, right? Okay, I'm just going to draw it as though the metal, everything has been removed. Okay, so yeah, and then I'm going to have this, and then a H here. And then the CH3 will remain below. This is the CH3. Okay, and then I'm going to draw like this. Okay, and then the CH3 will be here as well. Okay, and then the H will be pointing up, and then essentially this will be the OH. Okay, like this. Okay, yeah. Do you notice just immediately okay, do you sort of notice that by drawing it in this particular fashion, right, I have sort of predefined the stereochemistry about the alpha carbon as well as the beta carbon. Okay, what do I mean by I have sort of predefined the stereochemistry? So that means that because I drew it out this way, right, then, and because of the way the reaction is being positioned, or the reactant is being positioned in the transition state, this is the only possible stereochemistry which you can draw, and which kind of makes sense . Okay, so I hope you can sort of come to terms with that. And then right now, I'm going to draw a Newman projection, okay, on this. Okay, so if I'm going to draw a Newman projection, that means that I'm going to put my eyes over here. Okay, going to put my eyes over here on to draw the Newman projection, and you will be able to see what I would want you to picture and how it ends up with the syn. Okay, so I'm going to have this, a circle here. Okay, so right in front of me, I have a H here. Okay, and I have a CH3, okay, and then I have a OH. Okay, then right below I have CH3 here. Okay, then I have the H, and then the carbonyls. Okay, like this. Yeah. So if I'm going to do a rotation, which I'm not sure. Okay, so maybe without doing the rotation first . Okay, can I draw out the same Newman projection for the syn on the drawing here . So I'm just going to maybe draw in green, okay, so that you might be a little bit more convinced. I'm going to put a triple equivalence. Okay, so again, I'm going to put my eyes over here, okay, to draw it out so that it's so-called fairer . Okay, I'm going to put my eyes here to draw this out. Okay, so I'm going to have this like this. Okay, so now the CH3 is pointing below. Why is the CH3 pointing below, you might be wondering, because the H is here and then the H is here . Okay, I didn't draw in the H, so you have to visualize it yourself. And then this is the OH, and then this is the H. Okay, and then right below I have the H here. I have the CH3, and then I have the carbonyl. Okay, so now I want you to take a second, spend a bit of time to check out for yourself, right, whether these two Newman projections are the same. Okay, so this is equivalent. Yeah, whether these two are the same, the green and the red one. Okay, can you see that they are actually the same thing? Okay, so why are they the same thing? So I can get from the green to the red one by simply rotating both by 120 degrees to the clockwise. Okay, can you see that? Okay, so no tricks. Okay, maybe you can stare at it for a little bit longer to convince yourself. Yeah. Okay. Yeah. So they are exactly the same thing. Yeah. So this is how we predict the products. Again, if you are always not convinced, it is often good to convincing yourself by drawing out the relevant 3D confirmation. Okay. Yeah. Next. Okay, I realize I have been talking a lot, but I haven't been answering the question. So I have to draw the anti-product, right? Okay, might be obtained from the Z enolates lah. Okay, so how do we get the anti-product? Okay, so basically, right, my Z enolate is fixed. Okay, so that means that this particular portion is fixed. I cannot change it. Okay, but what I can change is my ethanol. So instead of reacting it like this, right, I can turn it the other way around. Because remember, the approach is from the top and bottom with near equal probability. Remember that? Yeah. So therefore, right, what I could be drawing is I should have this like this, and then like this, a H here. Sorry, I think it's not showcased very well. Okay, so maybe I should erase this portion. Okay, so what I could do is like this, then dot oxygen, and then like this. Oops, sorry, this is not working so well. And then this is the CH3. Okay, and then dot, and then this is the carbon, right? So now I have the CH3 above. This is the H, and then this is double bond O, and then the M, and then this with a plus, and then L. Okay, and this is the transition state we're talking about. Okay, so therefore the stereochemistry of CH3 remains. Okay, but OH will now be pointing out towards you. So therefore it is called the anti-product. Okay, so if you really need me to draw it out, so the anti-product will then be like this, double bond O, and then projecting inwards, and then like this, and then projecting out towards you. Okay, OH. Okay, yeah, so this is the anti-product which you should be drawing. And then why the syn product predominates in this reaction? Okay, so you notice that in the transition state, right, there is unfavorable 1,3 diaxial interaction between the axial R and the CH3. So because of that, the transition state leading to the anti-product is of a higher electronic energy as compared to that of the transition state leading to the syn products. Yeah, so because it's of a higher energy, so therefore the activation barrier leading to the anti-product is higher as compared to the syn product. Yeah, so therefore the syn product predominates in this reaction. Okay, then for part 2, draw the two possible products when E enolate is used instead to react with ethanol. Okay, so I'm going to draw the two products when the E enolate is used. Okay, so first of all, right, you know that if E enolate is used, you must ensure that the R and the CH3 is in the cis position, right? So therefore, the transition state should look something like this. I'm just going to draw one of them out, and then the other one will be details. Okay, so it's R, and then down, and then like this, and then this will be a H, and then the CH3 is here. Okay, so I'm just going to use the same one. Okay, so I'm going to dot O, and then dot the carbon here, and then I'm going to draw a H here. Then this is a CH3, and then double bond O, and then M, and then L. Okay, so this is the transition state we are talking about. Okay, yeah. So with that, I'm going to get the syn and anti-products out. Okay, so I'm just going to draw it below. So the first product is like this, O, and then this will be projecting outwards. Okay, so the CH3 will project outwards. Okay, and then for this transition state, I'm going to get the anti-product. Okay, so this is the transition state leading to the anti-product. And this is actually favored because of minimal 1,3 diaxial interaction. Okay, so I'm going to get the anti-product from here. Okay, yep. And then for the other transition states where I'm going to swap the two, so what I'm going to end up with is something like that, CH3, and then this is the CH3, and then the H double bond O, dot O, and then dot M, like this, L. Okay, so this transition state, I'm going to end up with the syn product. Okay, and this is not favored. This is not favored because of the unfavorable 1,3 diaxial interaction. Okay, so in our case here, the dominant product is the anti-product. So this is the dominant product. Okay, some of you might ask, is this the only product? Or I'm going to get a mixed. Okay, so the truth is you will always get a mixed. Yeah. Why is it that you will always get a mixed? Because the difference in the electronic energy of the transition state is not likely to be super high. Okay, there is a bit of a difference, but I mean, unless you can accentuate the difference, then you probably get about 99% of one over the other, which often is the case lah. I mean, that's often the case in asymmetric synthesis. But if you are not able to, then do expect a certain percentage of the minor products. Yeah, and then finally, you are supposed to suggest a suitable enolate C and aldehyde D that can be used to synthesize the following compound. And then I don't think this is of any huge difficulty because you notice that from this particular compound, okay, so I'm going to just erase this big portion here. Okay, the two likely candidates will be something like this over here. So this is the carbonyl, okay, likely to be like this, and then the other portion is likely to be over here. Okay, yep, and then notice that this is syn. Okay, it's syn, right? From what we have earlier on, this is actually the syn product, right? Okay, so because it's a syn product, I'm going to use the Z enolate. Okay, yeah, so it's the same thing. I'm just going to use the Z enolate. So I'm just going to draw it out for you to see. Okay, O double bond, and then like this. Yeah. Oh, sorry. I think there's some mistakes. So I shouldn't be drawing a double bond O because I should be using the metal bonded to the ligand. Okay, so I should be drawing OML2 and then double bond like this, the syn. Okay, and then for the aldehyde D, okay, what I'm going to use will be just this H C double bond O, and then I need to keep this chiral center. Okay, so the truth is because you notice that depends on the reaction, right? How do we accentuate the difference between the syn and the anti? Sometimes it's really by introducing a chiral center at the aldehyde, and it will help to a certain extent as well. But we won't go into details here. If you are really, really interested, you can read more about it in more advanced textbooks. Okay, so these are the two we'll use, C and D. Okay, C is the enolate, D is the aldehyde. Okay, so with that, we're just going to quickly move on to part C, which again is not a very difficult part. Often in H2 assessment in the various colleges, part C is something which come out quite common. Okay, so we have this George Wittig. Okay, so Wittig is a German chemist, so I think in German it's pronounced as Wittig, but I don't think I will use the German pronunciation. The Nobel Prize 1979. One of the most significant work is the Wittig reaction using phosphorus ylides. You don't really need to know what exactly is a phosphorus ylide, but the structures is given to you here. Okay, so from the structures you know that it's a carbene anion. Okay, so you can produce the produce the phosphorus elite by reacting the reaction between triphenyl phosphine and a primary or secondary alkyl halides. Yeah, this is something which is definitely very familiar to you, because remember that a phosphorus has a lone pairs of electrons. Okay, so a phosphorus can behave as a nucleophile, and then you notice that in the course of reaction, the phosphorus gain a positive charge, right? And then of course there's a leaving group X here, so you can envision it to be some sort of a nucleophilic substitution, which is being asked of you in part 1. What suggests the type of reaction occurs in step 1 and 2. Okay, so step 1 is nucleophilic substitution. You don't need to tell us whether is it SN1 or SN2, because it is not very important here. Okay, so what about step 2? You notice that step 2 uses an interesting reagent, but since you have already gone through carbonyl chemistry and hydroxy compound, then it shouldn't be a surprise, because this is essentially a reagent where the carbon is sigma bonded to a lithium. Okay, and remember what I told you earlier on, the concept of Coulomb. So this is delta plus, this is delta minus. So there's a reverse in reactivity of carbon. Instead of an electron deficient site, now it is an electron rich site. Okay, and the carbon gains a H from here, and that's how it becomes benzene. And then this reaction is driven by the formation of the lithium halide salts. Okay, so essentially this phenyl lithium serves as a nucleophile or a base to abstract out the hydrogen from the salts, and then this is none other than an acid-base reaction, which I think you should be able to tell as well. Yeah, okay, so it's an acid-base for step 2. And then you were told that in the Wittig reaction, a phosphorus elite is used to react with aldehyde or ketone to give an alkene. So react with aldehyde or ketone to give an alkene. Example of Wittig reaction is given below. Okay, so remember that a lot of the concepts you're going to encounter in H3, right? They will seem very familiar from what you have learned in H2. Yeah, so we will probably just take 1 or 2 steps beyond what you have learned in H2, but it will still be familiar to you. Yeah, and the carbon with the negative charge, right, it definitely has a lone pairs of electrons. If not, you wouldn't have the negative charge. So you do expect the first step to be some form of a nucleophilic addition kind of reaction. So I'm going to expect a nucleophilic kind of addition. Okay, and then of course you don't get this straight away lah. Yeah, so the first step is a nucleophilic addition. Okay, and then you are supposed to draw the mechanism or propose a mechanism to the above reactions, given that the reaction occurs via an intermediate with 4-membered ring. Okay, so now we shouldn't be proposing mechanism too far away from what we are used to. So now let us try to perform a nucleophilic addition first, and we see how it goes. Okay, so when we try to perform a nucleophilic addition reaction, so what we're going to get here is the ring here, going to get an O minus. Okay, and then of course we have a carbon here with a CH3, and then again I'm going to have a phosphorus here with 3 benzene rings. So I'm going to just put it as phenyl. Okay, so I'm going to let pH, okay, sorry, pH be the phenyl ring, C6H5, C6H5. Okay, yep, I'm going to let pH be C6H5. Okay, now this has a plus charge which is not being removed. Now, are you able to now see the potential appearance of the 4-membered ring? Something like this. Okay, I can just close this loop, right? How do I close this loop? Simply by a Lewis acid-base reaction. So this lone pair would then attack the phosphorus. Okay, so it's as simple as that. Okay, so with that, I'm going to form the 4-membered ring, and then okay, so I'm going to form the 4-membered ring. Okay, remember that it helps if you simply just follow instructions. So most of the time students didn't get it right because they don't follow instructions and they just try to do it their own way, and then it end up not really getting what you are being asked to do lah, right? Okay, then do you notice that this particular portion, the CC double bond, okay, I'm highlight in yellow, it's essentially this portion, okay, this portion, and then this particular portion with a P double bond O is essentially over here. Okay, yep. So because of that, how can I end up with the products? Yeah, simply I can break anywhere I want, but I need to form a PO double bond. So maybe this is a good way to form the PO double bond. And then I need to break the PC single bond in order to form the CC double bond. Yeah, some students might ask, can I do it the other way around? Yeah, you can. This is not the only way. Okay, so if you wish to, you can break the other way around. You can break it this way as well as this way. It doesn't really matter. It's really up to you. Okay, so with that, we have come to the end of the review for question 11. So do look out for future videos on reviews of the remaining questions.